Hello and welcome to my tutoring video. My name is Rakshan and I am a second-year biomedical engineering student. Today I'll be covering stoichiometry as part of the Chemistry 1125 course, which is a common gen ed requirement for engineering students. Let's begin. Stoichiometry often involves finding an unknown quantity of one substance given a known quantity of a different substance. So let's say we have substance A and substance B. We have a known quantity for substance A and an unknown quantity for substance B. The known quantity for A may either be something such as mass, volume, or number of particles. The same goes for the unknown substance B. What links the known and unknown values together are the amount of moles between substances A and B. For example, we can find the number of moles of substance A using either the mass, volume, or number of particles of the known quantity for A. We can use this given a balanced equation of the reaction, the number of moles of substance B. And using that, we may then find either the mass, volume, or number of particles for substance B. Let's go through some examples. Okay, so for our first example, we have 10 liters of nitrogen gas react with excess hydrogen gas. What volume of ammonia is produced? So we're given a volume of nitrogen gas, and we have excess hydrogen gas, which means we don't need to worry about the amount of hydrogen that is used. We are looking for the volume of ammonia. That is our unknown value. So the first thing we need is a balanced equation for the reaction. So we have nitrogen gas reacting with hydrogen gas to produce ammonia. So we see here that we have two nitrogens on the left side and one nitrogen on the right side. That means the ammonia needs to have a 2 coefficient. And we now see that we have 6 hydrogens on the right side, therefore we need to have 6 on the left side. So we have 2 currently, so we multiplied by a coefficient of 3 to get 6 hydrogens. Now we have a balanced equation. Now we need to find the amount of moles of nitrogen in the reaction. So first we will need to convert the amount of liters of nitrogen into its number of moles. And typically in questions like this, we would assume standard temperature and pressure. So we have 10 liters of nitrogen gas, and we want to convert this to moles. So we are going to multiply this by 1 mole divided by the amount of liters to cancel out liters. The amount of liters in 1 mole. At standard temperature and pressure, that is 22.4 liters. liters nitrogen gas. And this is 1 mole of nitrogen. The next thing we will need to do, so this will give us the amount of moles of nitrogen. We will need to then convert it to the amount of moles of ammonia. So we will multiply this by 2 moles of ammonia, because we have a coefficient of 2 in the balanced equation. And over here it's 1 mole because our nitrogen's coefficient is 1. So 2 moles of ammonia over the 1 mole of nitrogen. This will cancel out the moles of nitrogen in the mathematics. The next thing is so we are looking for the volume of ammonia, so we will multiply this by the standard temperature and pressure moles to volume ratio. So we'll multiply it by 22.4 liters of ammonia over the 1 mole per 1 mole of ammonia. This will cancel out the units of ammonia moles. So when we calculate this, once the calculation is complete, we find that we have 20 liters of ammonia produced from this reaction. For this next example, it says, given excess iron, what volume in milliliters of oxygen gas is required to produce 23.4 grams of iron 3 oxide, and that's Fe2O3. They give us the molar mass and assume a standard temperature and pressure. So we have excess iron, so we don't have to worry about that quantity. We are looking for the volume of oxygen gas in a reaction between iron and oxygen, and the given value is 23.4 grams iron oxide is produced. So the first thing we need is a balanced equation. So to produce iron oxide, we need to react solid iron with O2 gas to produce FeO3. Okay, so Fe2O3. So here we see that we have on the left side 2 atoms of oxygen and on the right side 3 atoms of oxygen. In order to make this balanced, what we can do is multiply each side by the opposite number. So over here, this O2 we multiplied by a coefficient of 3. That gives us 6 oxygens on the left side, and in order to have the same value on the right side, we multiply iron oxide by a coefficient of 2. So we now see that we have 4 iron atoms on the right side. So to make that equal, we add a coefficient of 4 for iron on the left side. So we are given the amount of grams of iron oxide, so what we need to do is convert that to moles first. So we have 23.4 grams of iron Fe2O3 iron oxide. To convert this to moles, we multiply it by, since we have a value coefficient of 2 here. We multiply it by 2 moles no. We are converting from grams to moles, so we don't use the coefficients yet. That's for the moles to moles conversion. So first we convert from grams to moles, so we multiply it by 1 mole of Fe2O3 and divided by the molar mass of iron oxide is 159.69 grams. And then that will get us the moles of iron oxide. So the next thing we need to do is convert this to the amount of moles of oxygen, which is what we are solving for. So we have a coefficient of 3 on oxygen, so we multiply this by 3 moles of oxygen and divide by the amount of moles of iron oxide that we have. That is 2 moles. Next, we need to convert the moles of oxygen into volume in milliliters. So, we multiply this by the STP conversion for volume and moles, from moles to volume. So that is 22.4 liters of oxygen divided by 1 mole of oxygen. And since we want our volume in milliliters, since the volume is in milliliters, that is unclear. We need to convert this into milliliters of oxygen. So we multiply it. So this is, there are 1,000 milliliters in a liter. So we use this conversion, 1,000 milliliters over 1 liter of oxygen. And this will get us our answer. So once we calculate our answer, we get a value of 4,923.45 milliliters of oxygen. And if we were to use significant figures, at the start we have 23.4 grams, that is 3 significant figures. So we would make this have 3 significant figures. Milliliters of oxygen. Also, one important thing to note is that if the molar mass is not given, then you will have to find it using the atomic masses given on the periodic table of elements. And now for one final example. This example states, given excess hydrogen gas and the following balanced equation, how many molecules of H2O are produced from 4.30 grams of O2? And they give the molar mass of O2 as 32 grams per mole and Avogadro's number. So here they say excess hydrogen, so we don't need to worry about the amount of hydrogen that's present. They give us a balanced equation right here, and we are looking for the molecules of H2O, that is our unknown, and we are given the mass of oxygen in grams. So the first thing we'll need to do is convert the mass of oxygen into moles. So we do that by taking the mass, 4.30 grams of oxygen, multiplying it by 1 mole, and then dividing by the molar mass, 32 grams. So that'll give us the amount of moles of oxygen. So we then need to convert the moles of oxygen into moles of H2O. So the values here are 2, a coefficient of 2 for H2O, so we multiply by 2 moles of H2O, and then this is moles of oxygen. Then we divide it by the moles of oxygen, and it is 2 moles given the coefficient, 2 moles of oxygen. The next thing we'll need to do is convert the moles of H2O into molecules of H2O. So we know that from Avogadro's number, there are 6.022 times 10 to the 23rd molecules of H2O in 1 mole. This goes for any particle, not just for molecules of water. And once we plug the value into a calculator, we find that there are 8.09. We go to 3 sig figs because the starting value has 3 sig figs, times 10 to the 22nd molecules of H2O are produced from this reaction.